Okay, so I just want to reiterate what Hopital's rule says. First of all, it says if you have a certain type of indeterminate form, then rather than taking the limit of the ratio of two functions that form one of those indeterminate forms, you could take the limit of the ratio of those two functions' rate of change, meaning their derivatives. Okay. What are the two indeterminate forms for which the Hopital's rule applies? 0, 0, and yeah, plus minus infinity over plus minus infinity, which I'll usually just from here on out say infinity over infinity. It's any combination of those pluses and minuses. Okay. Those are the two situations for which Hopital's rule immediately applies. Okay. What does the graph of the natural log of x look like? Well, it looks like this. As I go to infinity, what does the natural log do? It rises oh so slowly towards infinity, right? As I go far to the right, my natural log curve is increasing. That's for the ln of x. What about my cube root of x? What does the cube root of x look like? It's supposed to go through the origin there. It looks something like that, right? As I go far to the right, what's it doing? It's rising, arbitrarily large. So both of these limits are going to infinity. This does have indeterminate form, infinity over infinity. Okay. And again, it's got a function that I'm not really comfortable working with limits with, the natural log, so let's go ahead and apply Hopital's rule. It applies. I think we should apply it. So this gives us the limit as x approaches infinity of 1 over x all divided by 1 over 3x to the 2/3. So let's look at this. So now this has indeterminate form. What happens to this numerator as x gets large? Approaches 0 all over. What does this denominator do as x gets large? It has an indeterminate form, 0 over 0. Does Hopital's rule apply? Should we apply it? Okay. So don't write this down. I'll apply Hopital's rule again. We get the limit as x approaches infinity of minus 1 over x squared, all divided by, holy cow, 2/3, 2 minus 2 over 9x to the 5/3 when you apply Hopital's rule again. We still have indeterminate form 0 over 0. Should we keep going? No, I think what's happening here, I think things are getting more complicated as we continue, don't you? Okay. So remember, Hopital's rule, so you could keep going, but you'll never get, whatever work you do if you want to get to the answer from here is equivalent to the work you would have done up here. So just because Hopital's rule applies doesn't make it a good idea. Be careful with that. Okay? This still has indeterminate form, but notice it's also one rational function over another. And we know how to deal with those. Let's in fact clean this problem up. I'm not applying, this is why I want you to tell me when you're applying Hopital's rule, because I need to know whether you're doing algebra or calculus. I'm not applying Hopital's rule. I'm just going to go ahead and say that's 1 over x, and how do I divide by a fraction?
Multiply by its reciprocal.
Yeah, we multiply by its reciprocal. Invert the denominator, specifically. Invert the denominator and multiply it. So this gives me 3x to the 2/3 over 1, which is the limit as x approaches infinity of, well, let's see here, that would be 3 over x to the 1/3. What's the exponent on this x here? Okay. So it's 1, but I can think of it as 3 over 3, right? Okay, so this gives us 3x to the 2/3 over x to the 3/3, right? How do you divide by exponents? Subtract, so let's see here, we can say that's 3x to the 2/3 minus 3/3, which gives us 3x to the minus 1/3. Gives us 3 over x to the 1/3. It's all right. It's all right. Oh, don't beat yourself up. All right. We get this. This limit comes out to be 0. So In this tug-of-war match between a numerator that was getting large and a denominator that was getting large, who won? Well, the denominator did. It brought everything down to 0. Of course, you can develop a problem that gives you every number in between. That's why these are these indeterminate forms. All right. The next ones are the indeterminate differences. Arbitrarily large minus an arbitrarily large. Where is that going to take us? Who knows? You don't know. So, what do we want to do? Well, the trick here is to try to rewrite it as a quotient by either getting a common denominator or rationalizing or factoring out a common factor. Okay. Should I add anything else? I guess I could try, we could probably add to this, multiply by the conjugate over itself. Sometimes that'll help too. The indeterminate differences are a little squishy. There's not a lot of tricks. Each one's kind of unique. Okay? But those are all things that would possibly help when you have an indeterminate difference. Okay? So let's look at this one. Which of these three do you think would be easiest? 4. Common denominator, rationalization. Right, we're trying to write it as a single fraction. What's going to be easiest? Yeah.
It would be completely wrong, but secant.
Okay.
If you do the identities for
Uh-huh.
and
Keep
tangent,
going.
isn't that 1 over cosine minus sine over cosine?
Ah, so this one not only is it probably the best option to get a common denominator, but this one already has an inherent common denominator ready to go, right? So we've got the limit as x is approaching pi over 2 from the left of 1 over the cosine of x minus the, that's kind of silly looking. 1 over the cosine of x times, minus the cosine of x. Folks, I apologize. I've got sinus headache. Today I've got an excuse for other things. I've got sinus headache today, so I'm not feeling good. All right. As opposed to usual, it's not just the usual. Coming it up. All right. Now we can write this as a single fraction, right? So what is this as a single fraction? It's 1 minus the sine of x all over the cosine of x. Look at this. This now has indeterminate form what? This now has indeterminate form what? 0 over 0. You see that? Sine of pi over 2 is 1, so you get 1 minus 1 in the numerator. Cosine of pi over 2 is 0. Okay. Oh, I guess, by the way, we never actually identified the original indeterminate form. We should have done that, right? Because we're getting ready to apply the Hopital's rule. I mean, now it is clear that the Hopital's rule applies, but why did we get started on this train? Well, what's the secant what's the limit as x approaches pi over 2 from the left of the secant of x? It's infinity. And what about as we approach tangent? It's also infinity, so we end up with infinity minus infinity. So I didn't say that. We should have identified the indeterminate form here initially. And it's one of these differences, which is why we said, okay, or Amy said, let's try to write it as let's try to get a common denominator here. All right, questions on this so far? So now we're ready to apply L'Hopital's rule, and we get the limit as x approaches pi over 2 from the left of minus cosine of x all over minus sine of x, which you can argue two ways. One, you could go ahead and just call that cotangent and give the limit, or you could talk about a 0 divided by an arbitrarily small, let's see here, a 0 divided by 1. I guess we could just do direct substitution here. Okay. So either way, either rewriting this as cotangent or just evaluating through direct substitution, which I think we'll do. So this gives us the cosine of pi over 2 over the sine of pi over 2, which is equal to 0 over 1, which equals 0. Okay? Folks, can you always say that an indeterminate difference will come out to be 0? No. Otherwise, we would just have said so.